So these are the kinematic equations, and these can be exactly written in rotational motion. So for example, we saw this one earlier today. We wrote it as omega f is equal to omega I plus alpha t.
Mm-hmm.
So if you don't remember these, I would write those down and either memorize them or just keep them on hand if you're doing homework or whatever, because these are always useful. So instead of distance, we're working with arc. So if we have some circle, um, and this is our theta. This uh, arc right here is kind of like our distance. This is our um, what we call it arc. So usually this is written as, let's change pen colors again. So this is written as is equal to delta theta is equal to delta arc divided by the radius. So this would be our r. Okay. So basically, if we have the arc length, radius, or theta, we can kind of convert between these two.
Yeah.
So this is kind of the idea. If we start here and then move all the way over to here, we can, you know, we have motion. Woohoo!
Yeah.
We can do physics.
Yeah.
um, okay, so this is the equivalent of position in normal 2D kinematics. So the next part is kind of what is velocity in um, rotational motion. Do you have a guess? If this is position, what would be velocity?
If that's position, it will be velocity.
Yep, and we write velocity as omega.
It would be it will be the position times s. Uh, wouldn't it be? Or over s
Um, so do you remember what velocity is in normal physics?
is basically like the speed. So it's like time over distance,
Yeah, other way around. Distance
distance
over
over
time.
time. Okay.
Yeah. So
So this one would be
yeah, then we usually write this as delta x over delta t, where x is the position.
alright.
So how would we write it in rotational motion?
We would put the that s is speed
S is arc. So it's
of
kind
the
of
arc length.
confusing. It's like it's this red. It's like the distance around a circle is arc.
Yeah, yeah, the arc length. All right. Um, so would it be because we don't have any time? That's the only thing that's messing me up.
We can introduce time. Let's just say we have delta t. We have some change in time.
So would it be the arc length over time?
Close. It's not going to be the arc length. Um, well, actually, I can see where you would say that, and we'll talk about arc length in a bit with rotational motion, but it's going to be the angle divided by time. So it's basically like we rotated through this angle in some amount of time.
Yeah.
But you are right. There is some motion at the arc length, and we do need to account for that. And the way we do that is let me get rid of this real quick.
So it's the angle over time, right?
Yeah. Yep. And do you know what this triangle means? Delta.
Yeah, that means wait, I remember seeing in the other kingdom delta x.
Yep.
It's like oh the displacement, right?
Yeah. Yeah. That's another way of saying it. I like to think of it as change. So this is the change in the angle and the change in time. Um, yeah. Okay. So, but yes, displacement is another way of thinking about it. Okay. So, but now the kind of question you pose is like, how do we track the speed or the velocity at the arc length? If we're at, this point here, and we end up at this point in some amount of time, well, clearly there's a speed happening.
Yeah.
So the question, so it's like, how do we work with that? And that is a great question. And let me pull up my thing just so I have it right. And you are right. So, but I'm gonna call this instead of omega as like the rotational speed, I'm gonna call it the tangential velocity. And do you know what tangential means?
Um, no, it sounds familiar.
Yeah. So tangent usually means we have a line that only touches the circle at one point. So I'll do my best to kind of draw that. It's kind of like this. So it
Oh
doesn't
yeah,
it
yeah, I
doesn't
remember that. I
intersect.
remember that. Yeah.
Yeah. So we basically say that there's kind of like a velocity at that's tangent here and tangent here. So this will be like v1, this will be v2 or something.
Hmm.
Yeah. So that's tangential. Yeah, so we call it vt. And you are right. This is going to be delta s over delta t. So very good. Good, good. I'm glad you caught that. Um, However, we're not often going to be given the arc length just like straight off the bat. So we kind of need to calculate it. So based on what we've written so far, is there a way that we can is like if we were given other information, could we calculate the arc length?
Um, yes, if we're given the radius and if we're given the angle.
Exactly. Exactly. So this is more often written as um yeah, delta theta times r over delta t. But even, I'm just going to rearrange this one more time. This is often written as r times delta theta over delta t or r times omega. See how that works?
Yeah.
Yeah. So this is the relationship between these two things is the radius.
Wait, what does omega stand for again?
Omega is specifically just the angular rotation. So we
Uh,
don't we don't we're not worried about how far away it is from the circle. If you kind of imagine like a turret turning left and right, you know, we don't care about necessarily how far away the target is. We only want to know that the turret has rotated 20 degrees or something like that.
yeah.
Yeah. Okay. Good so far?
Yeah, I'm good.
Okay. Well, actually, let me ask you this. How would we write, well, this is kind of a trick question, but how would we write acceleration in angular? So if we're trying to use omega.
Um, um, oh, um, um, I don't have no idea.
Okay.
What is it like a? Is it like a?
So
Yeah, I don't know.
compare it to normal physics because it's going to be the exact same thing. We're just using a different position component. So we're using angle instead of meters. So how do we do acceleration in normal physics?
Um, acceleration is time.
There's time. Yep.
Um,
So what is the definition of acceleration?
How fast you speed up.
Yeah, and in particularly, that is a change in velocity.
Oh yes, yes, yes. Initial velocity subtracted by final velocity.
Yeah, other way around. Yeah, but you have the idea. It's this. It's this equation right here.
Yeah,
But I'm just gonna write it as delta v. It's delta v over delta t. We don't have the delta here, but that's usually because there's a change in time being implied.
yeah.
Um, but this is the idea for normal 2D kinematics. So how can we apply that to rotational motion
We
if
would
we have
put
alpha as our rotational symbol?
so it would be uh initial final velocity minus initial velocity, um, and then like the arc length would be added, something like that.
Um, well, maybe I didn't quite follow, but what is our velocity when we're talking about rotating around a circle?
Oh, torque.
Nope. Torque isn't a velocity. It's like force over a distance or force times distance. Quite. All I was looking for here is omega.
Oh yeah, yeah, yeah. Oh my god. All right.
Yeah. Sorry, I wasn't. I'm not. I wasn't trying to confuse you or anything. It's just omega is our rotation over some time. So our angular acceleration is the change in omega over the change in time. So that's this is basically all the basics of rotational motion.
Yeah.
The last thing that we could talk about is centripetal acceleration and centripetal force. Have you heard of those?
I don't believe so.
Okay. Um, so I kind of well, I forget what these things are called. Have you ever been on one of these like playground things where they have like the uh like poles like this, and there's one kid who's like running on the outside,
Oh yeah,
spinning it
moving it,
super
spinning it.
fast.
Yeah, yeah, yeah. I know what you're talking about.
Yeah. So have you ever like been on one of these and you're like hanging on for dear life? Like you're like almost out of strength because it's spinning so fast?
Yeah.
Yeah. So isn't that interesting? You have to apply your own force even though nothing is pushing on you. So let me ask you this. What's pushing on you? Is something pushing on you? Why do you have to pull so hard to stay on?
Because you're the more outside you're on, like the a force is pushing you outside.
So you made a good connection there. The further you are to the edge, the harder it is, right? If you're standing here in the middle, you're J chilling, right?
Yeah.
You're good. You're not even worried. This guy's freaking out. You're just like, what's going on? So yeah, so one component of it is going to be the radius.
Oh, because you're farther away from the center of rotation.
Yeah. So let me ask you this: if this guy, stops spinning, it gets bored or whatever, um, you know, and this stops spinning, is there still a force?
If it completely stops, no, there's not a force.
Right. Okay. So we've kind of got some idea that basically how hard you have to pull. So I'm going to call this F. Um, I'm going to call it FC because I know it's centripetal, but FC is um. So I'm going to use this symbol as proportional. This just means we don't know exactly what it is, but we know that some component of this is the how fast it's rotating and the radius that we're at. Does that make sense?
Yeah.
Okay. And if we were to actually like do the math and stuff, we would actually find out that indeed this is true. But the numbers are a little different. It's the centripetal force is equal to basically how heavy you are times the radius times omega squared. So really, how fast it's going really is impactful. So even more so than how far out you are, it's how fast it's getting rotated because it's squared.
Yeah.
Okay, so we are out of time. So I'll end my lecture for today. Um, but I do got time for any quick questions. So do you need any clarification for anything we worked on today, or?
No, I'm good. Let me just like write this the rest of it down.